This is Enceladus, Saturn's sixth largest moon. At first glance, it's easy to overlook. A frozen speck, barely 500 kilometers across, drifting silently through the vast gravitational domain of a gas giant. Compared to the colossal presence of Saturn, Enceladus seems insignificant. But in the realm of planetary science, appearances can be wildly deceptive, because this tiny, icy world has become one of the most compelling places in our entire solar system, and possibly one of the best chances we have of discovering life beyond Earth. Everything changed when the Cassini spacecraft arrived in the Saturn system. Before Cassini, Enceladus was little more than a curiosity. Astronomers knew it existed. They knew it was bright, extremely reflective, in fact, thanks to its surface being coated in fresh ice. But beyond that, it didn't stand out. It wasn't like Titan, with its thick atmosphere and methane lakes. It wasn't like Jupiter's volcanic moon, Io. Enceladus seemed quiet, still, frozen. Then, in 2005, Cassini flew past the moon and saw something that no one expected. Towering plumes, massive geysers, were erupting from its south pole. These weren't small jets. They were enormous. Columns of water vapor, ice particles, and organic material blasting into space at hundreds of meters per second. It was as if the moon itself was breathing, exhaling material from a hidden interior into the vacuum. In that moment, Enceladus went from a forgotten moon to one of the most important objects in planetary science, because those plumes meant one thing: there was liquid water beneath the surface, and where there is liquid water, the possibility of life suddenly becomes very real. Cassini didn't just observe these plumes from a distance. NASA made a bold decision to fly the spacecraft directly through them. This was risky. Spacecraft aren't designed to slam into high-speed particles, but the scientific payoff was too important to ignore. By passing through the plumes, Cassini could directly sample material from inside Enceladus without ever having to land. And what it found was astonishing. Water vapor, abundant and unmistakable. Organic molecules, carbon-based compounds, the building blocks of life. Molecular hydrogen, an energy source that on Earth is used by microbes living around deep-sea hydrothermal vents. In other words, Enceladus wasn't just wet, it was chemically active and possibly habitable. To understand why this is so important, we need to look at what life actually requires. Scientists often talk about three core ingredients: liquid water, a source of energy, and the right chemical building blocks. Sometimes a fourth is added: time. Life needs stability long enough to emerge and evolve. Enceladus appears to check all of these boxes. Let's start with water. The plumes alone confirm that water exists. But the bigger question was, how much? Is it just a small pocket beneath the surface, or something far larger? For years, scientists debated this. Early models suggested a localized ocean beneath the South Pole, a kind of subsurface lake. But as more data came in, a different picture began to emerge. By tracking tiny variations in Enceladus's rotation, its subtle wobble, known as libration, scientists realized that the moon's outer shell is not rigidly connected to its core. The best explanation? A global ocean. Not just a small reservoir, but a planet-wide layer of liquid water sandwiched between the icy crust and a rocky interior. An entire ocean world hidden beneath ice. Next comes energy, because here's the problem. Enceladus is far from the sun. Solar energy is weak. Surface temperatures are brutally cold, around minus 200 degrees Celsius. Under those conditions, water should be completely frozen solid. So why isn't it? The answer lies in Saturn's immense gravitational pull. Enceladus is tidally locked, meaning the same side always faces Saturn. But its orbit isn't perfectly circular, it's slightly elliptical. As it moves closer and farther from the planet, Saturn's gravity stretches and squeezes the moon. This constant flexing generates heat inside Enceladus through friction, a process known as tidal heating. It's like bending a paperclip back and forth. Eventually, it heats up. Inside Enceladus, this effect is powerful enough to keep the ocean from freezing and to drive geological activity. But there's more. Evidence suggests that at the bottom of this ocean, where water meets rock, hydrothermal vents may exist. On Earth, hydrothermal vents are among the most extreme environments imaginable, deep in the ocean, completely cut off from sunlight, and yet teeming with life. Microorganisms there don't rely on photosynthesis. Instead, they use chemical energy released from the planet's interior. If similar vents exist on Enceladus, they could provide both the energy and chemical gradients needed for life. And that brings us to the third ingredient: chemistry. Cassini's instruments detected a surprising range of molecules in the plumes. Simple compounds like carbon dioxide and methane. More complex organic molecules containing carbon, hydrogen, nitrogen, and oxygen. Over time, reanalysis of the data revealed even more. Phosphorus, a critical element for life found in DNA and cell membranes, was eventually identified. Together, these elements form what scientists call CHNOPS: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. These are the fundamental building blocks of life as we know it. Finding all of them in Enceladus's plumes is extraordinary. It means the moon has the raw ingredients necessary for biology, but having ingredients isn't the same as having life. For that, you also need time. And this is one of the biggest questions surrounding Enceladus. How long has this ocean existed? Is it a recent phenomenon, or has it been stable for millions or even billions of years? Recent studies suggest the latter may be true. Thermal models indicate that the heat produced by tidal forces could sustain the ocean over very long timescales. Observations of heat escaping from both the south and north poles suggest that internal activity is not only ongoing but widespread. This increases the likelihood that Enceladus has had enough time for life to potentially emerge. Meanwhile, even after Cassini's mission ended in 2017, when the spacecraft deliberately plunged into Saturn's atmosphere to avoid contaminating its moons, the science didn't stop. In fact, in many ways, it accelerated. Scientists are still analyzing the vast data set Cassini sent back. With improved techniques and better models, they're extracting new insights from old data. And then there's the James Webb Space Telescope. Recently, Webb turned its powerful instruments toward Enceladus and made another stunning discovery. The plume is even larger than we thought. Extending thousands of kilometers into space, it forms a Vishal cloud of material that feeds Saturn's E-ring, a vast, diffuse ring made almost entirely of ice particles from Enceladus. This means the moon isn't just active, it's shaping its environment on a planetary scale. It's influencing Saturn itself. And yet, for all we've learned, the biggest question remains unanswered. Is there life on Enceladus? Right now, we don't know. We haven't detected organisms. We haven't seen cells or direct biosignatures. But we've found something arguably just as exciting: a world where life could exist. A place with water, energy, chemistry, and time. All the ingredients needed for biology. And perhaps most importantly, a place where we can access that environment without drilling through kilometers of ice. Because Enceladus is already doing the hard work for us. It's spraying its ocean into space. All we have to do is go back and catch it. Future missions are already being discussed. Some propose orbiters that would repeatedly fly through the plumes with more advanced instruments. Others imagine landers that could touch down near the South Pole and analyze fresh deposits. There are even concepts for robotic probes that could melt through the ice and explore the ocean directly. Each of these ideas brings us one step closer to answering one of humanity's oldest questions. Are we alone? Because if life exists on Enceladus, even in its simplest form, it would mean that life is not unique to Earth. It would suggest that biology can emerge wherever conditions are right, that the universe may be filled with living worlds waiting to be discovered. And all of that from a tiny moon orbiting a distant planet. Enceladus reminds us that the most profound discoveries often come from the most unexpected places. What once looked like a frozen, lifeless rock is now one of the most promising habitats beyond Earth. And the story is far from over. Even now, more than a decade after Cassini's final dive, new discoveries continue to emerge. Old data reveals new secrets. New telescopes expand our view, and future missions promise to take us even closer. Somewhere beneath that icy crust, in a dark ocean warmed by the pull of a giant planet, chemistry is happening. Energy is flowing, and just maybe, something is alive. If that's true, then Enceladus isn't just a moon. It's a second Genesis. And the next time we return, we might not just be exploring a distant world, we might be meeting it.